All right. Okay, we're recording. So last time, actually before anything, one thing I really want to emphasize, and I brought this up at lab yesterday, it's really boring when I just stand in front of you and talk at you. I don't like doing just that, so I like to ask a lot of questions. I like to have student participation. I love when students ask questions because then it gives me a chance to break up what I'm doing. So don't be afraid to ask questions. In fact, just please do it. Please ask questions. And I always say, if I'm explaining something and something was unclear and you have a question about it, but you're too nervous to ask because you don't want to feel stupid or something, every time someone asks a question, half the people in the room have the exact same question, but everyone was too nervous to ask because they didn't want to seem stupid or something. So just do everyone a favor and ask the damn question. Because if you're misunderstanding, a lot of other people are probably misunderstanding, and it's better to ask when we're talking about it than later. Because otherwise it can get hard to go back and explain things. So please ask a bunch of questions. Let's do a quick check to see if the camera's still working. All right, looks good. Cool. All right, well, so last time, this is what we ended with. Hello world. Okay? That's how we ended it. And this is an example of output. The computer did something. We wrote a program, and then we said, okay, output some information. I mean, that's really all this program was. Output some information. Output what we would call the string hello world. The words, the sentence, whatever. Output that. Print it out. But today, we're going to learn a little bit more about, print. We're going to talk about it a little bit more. We're going to talk about values and variables, along with types. Now, for those of you that had lab yesterday, a lot of it's going to be review based on what you did in lab yesterday. And for those of you that have lab today, you're going to be very well prepared for lab today. So, before anything, here's what I want you to do. Let's start with chatting with each other again. I want you to talk to the people around you, partner off or whatever, and I want you to explain how you did, and if you didn't have breakfast, how you would have made or prepared breakfast for yourself in the morning. Explain it to somebody else, and then do vice versa. Seriously, do that, please. If it's quiet in here, you're doing it wrong. All right, who's brave enough to tell me how they did it? And I'm going to act it out.
Okay. All right.
Who's going to do it? Come on. Someone explain. Okay, tell me. Okay, I'm you.
Okay.
And you're making breakfast this morning. What am I going to do?
Do I give you all the steps?
Yeah, of course.
Walk to the fridge.
Okay, walk to the fridge. Where's the fridge?
The kitchen.
Yeah, okay. I'm in the kitchen. Okay, so where's the fridge?
There.
It's there. Perfect. Walk to the fridge. Okay, yeah.
So get the bagels and the cream cheese out of the fridge. Open the fridge first.
Oh, thank you. Okay. Because I can't. It's stuck. I can't. Okay, open it. Wait. Oh, lift my hand. Okay, yeah. I gave him that one for free. Lift my hand, yeah.
Put it in the handle.
Put it on the handle of the fridge. Okay, good. Open it. All right. Okay, it's open. Yeah. Now what? The bagels are there. Okay, yeah, you're right. I found them. Got them. Cream cheese is in the door. Perfect. That's where I keep mine too. Yeah. Yeah. Okay. Yeah. Put it in the counter behind me. How far back? How much?
One step.
Perfect. Nice and small kitchen. I like it. Easy to get around. Now what?
Open the bagel.
You know what? I'm actually going to just close the fridge door. Yeah. Don't want to waste, right? Okay. Open the bagels. Okay. Wait. Okay. Yeah. Okay. Yeah. Take the little tab off and open them up. Yeah. Yeah. Okay. Take it out. Yeah.
Take the bagels out.
Yeah. Okay. A bagel. Yeah. Separate them. Is it like the pre-cut kind? Oh, those are those. I mean, half the time they tear, but whatever. Okay. Yeah. All right. I got it.
And put it in the toaster.
Put it in the toaster. Where's the toaster?
Next to the fridge.
Next to the fridge. Okay. So on the right of the fridge. So just over here. Okay. Put it in. Yeah.
Turn on the oven.
Turn on the oven. Okay, we'll stop now because now I'm just being mean too. So if you were all describing something more or less the same, you were, and I'm not being silly with my terminology here. I'm being very precise. That is an algorithm. It is. Just like directions on how to get to the university from where you are, that would be an algorithm. How to bake a cake, that's an algorithm. Instructions how to make breakfast, that's an algorithm. It's a step-by-step process that something or someone can follow to achieve something. All right, so that is an algorithm. Now, we can play a game of abstraction of like, well, how detailed does it need to be? Right? Like I was being kind of nasty with him, being, oh, where's the fridge? How do I open the door, right? I mean, if you were talking to another human, you'd say, get the bagels out of the fridge, put them in the toaster. Like it'd be a lot easier to communicate because humans operate at a fairly high level of abstraction. We don't need to go into all the nitty-gritty details of like put your right foot in front of your left foot. We don't need to think about neurons firing and ion pumps and muscles contracting and all this nonsense. No. We don't think on that level. All of that's involved, but we're operating at a much higher level of abstraction. And there's like everything in between, too. So I was being a little nasty by playing the game of how deep can I go. But that is an algorithm. And the funny thing is, like, everyone thinks of computers today, everyone thinks of computers as like those boxes that you're looking at, or your phone, whatever. But the word computer is a far more general term than just those boxes that we use to go on the internet. A computer is any device, anything that can perform a computation. And how we define computation, well, that's a little outside the scope of the course because it can get there's nuance to it. But even something as simple as like a safe with a lock, that's a computer. It doesn't need to be electronic. It could be purely mechanical. That is a computer. All of you, your brains are capable of computation. You are a computer. Sometimes people will be like, it's not really nice to call a brain a computer. It is, by definition, a computer. There's no ifs, ands, or buts about it. It is. Anyone who wants to argue the semantics of it, they are wrong. It is a computer. Now, okay, so we talked about an algorithm. You came up with that algorithm. Algorithms also, there is a difference, but for the most part at this stage we could think algorithm, program, same idea. Algorithm's a little bit more general. It's just a series of steps. Program is a little more specific for, like it's for a computer. But that's like a program. Now what's debugging? Well, debugging is what you're going to be doing most of the time when you're programming, like I was saying yesterday. Most of the time your code's going to be wrong. Like, when I say most of the time, I really mean like every time it's not right, it's wrong. And there's going to be a lot of times. You're going to hit run 100 times and it's going to be right once type thing. Like you're going to be wrong a lot. So you need to debug. What's wrong? Some bugs are caused by like, I used the programming language wrong. Some bugs are caused by like, well, I described how to solve the problem wrong. Like imagine he were to tell me go to the, I don't know, go to the garbage can and grab the bagels out of there. Like, well, that's not a great idea. That probably won't work very well. I don't keep my bagels in the garbage can. So debugging is the process of finding what's wrong and fixing it such that your program is correct. So realistically, you definitely should be expecting to be debugging a lot. Most of what you do when you're programming is debugging. Get used to it. I'm not saying that to be pessimistic. I'm saying that because that's the way it is. If you sit down and you expect to get it right the first try, you're going to have a very bad time. And yeah, like I said, you're going to be wrong every time before you're right. You're going to be wrong a lot more than you're correct. And that's normal. This is the case whether or not you are a new programmer or a programmer who's been programming for 40 years. That's the way it is. So have you seen any Python errors yet? Have you, I mean, maybe in the lab, if you were playing around with Python, have you seen any errors or anything yet? Raise your hand if you have. Yeah, right? I even showed in the lab one the other day, yesterday. Sometimes bugs will come up with an error message. And the error message will try to tell you what's wrong. Now, Python's error messages are pretty helpful, but there is a little bit of like experience and like understanding that you need to have. But if I ever see an error message I don't understand, the first thing I do is I just copy and paste it into Google. Because, I don't know, I think in even like some modern IDEs, if you highlight an error message, it'll ask, do you want to Google this? Because somewhere else will be able to explain it better. Because like a one little sentence is a lot harder to understand than like a nice, well description of what the heck's going on. And it gives you an idea of what's wrong to help you solve the problem. Sometimes the error messages can be like, there's a mistake on line 14. Great. Sometimes the error messages aren't that clear. And sometimes you have a bug in your code, but you'll see no error message. And you don't notice that there's a problem. And that's bad. So languages, if at any time you have any questions, comments, concerns, thoughts, anything, just raise your hand, please. Don't be afraid to interrupt. All right, so what is a natural language? Well, a natural language is what like we use. English, for example, is a natural language. It's a language that's, evolved over a long time, and we use it to communicate. And there's a lot of like interesting like prose and like rhetoric and like ambiguity. There's a lot of like interesting stuff we can do with natural language that we use for things like rhetoric, right? Like it's great. We've got a lot of flexibility with these languages. But then there's formal languages. And a programming language like Python is a formal language. Like mathematics, there's formal languages there. And a formal language is a little bit different. It's going to be a lot more strict. It's still used to communicate ideas. But it's far stricter in its structure and how you use it. And there is no room for ambiguity. If there's any ambiguity, there's a problem. So that's what a formal language is. And formal languages, the reason ambiguity is such a problem is like, with English, I can like describe anything that the English language allows me to describe. But with a formal language, there might be like statements. When I talk about formal languages, I'm only very briefly going to talk about it here for the course. It might come up a little bit later in the semester, but this is like a fourth year topic, right? So I'm just giving you an idea of where this could go to give some context to programming. It's funny, in a computer science degree, you don't learn the basic foundational stuff until like fourth year. It's weird. You kind of have to somehow magically know everything before you can do the intro. It's weird, but whatever. So with a formal language, what's interesting is you can't actually describe everything with a formal language. There are provable limitations. And just a simple explanation, now I can say this with English and whatever, it's kind of like a fun thing to say. But imagine this statement, and this is where things come up a lot, is whenever you have self-reference, weird stuff happens. The statement, this statement is false. What does that mean? It's wrong. So this statement is false, and you're telling me it's wrong, which would therefore mean it's correct, right? But if it's correct, then it's false. But if it's false, it's true. And then if it's true, it's in fact false. Raise your hand if you don't quite see the point I'm making. You would know if you saw the point I'm making. Okay, I don't believe you. Everyone understands completely, fine. This statement is false is a funny thing because, like, here's another example, okay? Raise your hand if you know who Pinocchio is. Perfect. Pinocchio, for those of you that don't know, it's an old, like, Italian story. I think it's Italian, I could be wrong. Of a little wooden puppet, and if he ever lies, his nose, what? It grows, right? So whenever Pinocchio lies, his nose grows. What would happen to Pinocchio if he says, my nose will grow now? What would happen? He would explode. Yeah, that's a good answer. Think about it. If he says my nose is going to grow now, that means he's lying. Right? Because, okay, he's saying my nose is going to grow now. Okay? And if it grows, that means he was lying. No. What am I doing wrong here? Well, it's Friday, right? Okay. My nose is going to grow now, okay? If it doesn't grow, that means he was lying, meaning his nose should have grown. But if his nose did in fact grow, it means he was actually telling the truth. See, half the people are like, yeah. The other half of the people are like, yeah, totally. If Pinocchio says, think about it. I'm Pinocchio. I sit here and say, my nose is going to grow. If it grows, I was telling the truth. But if Pinocchio tells the truth, his nose doesn't grow, meaning it should never have grown in the first place. But then he would have been lying by saying my nose will grow and it didn't grow, meaning it should have grown. But if it grows, it shouldn't have grown. And if it doesn't grow, it should have grown. But if it doesn't, if it does, we kind of get stuck in this like loop of impossibility. You can't resolve that statement. It doesn't make any sense. Now you and me, we can say that and we're like, oh yeah, whatever. Did anyone, now this is older now. Anyone in here ever play Portal 2? Okay, yeah, you played Portal 2. There's a reference to this joke where the little robot, but the robot is so stupid that they tried to play this joke on him, like, oh, if you say this to a robot, they'll explode. But the robot, what was his name, like Weasley or Wheatley? They said it to him to say it, and he's like, what's the problem? It's fine. And he carries on. And so it was the joke that the robot was so stupid it couldn't even, anyways, it's whatever. It was really funny. So there are actual limitations to formal languages. There are actual limitations. Well, it's actually not even really a limitation of a formal language. If you take a step back and think about this in the broader world, it almost sounds cliche to say, but it's true. There's actually like these limitations with our universe in that there are things that are like unresolvable like that, which is kind of fun. All right, there is some terminology. There's going to be a lot more terminology than just this. There's a lot of jargon that computer scientists and programmers use. I'm going to try to make as much of it as explicit as possible. If I start using jargon, for those of you that don't know, raise your hand if you don't know what jargon means. Okay. Jargon is just a fancy word that means like the computer scientists use special words to have special meaning that if you don't know, you don't know. So like when I say I/O, right? I say that to another programmer, they know exactly what I'm talking about. If you're not a programmer, you're probably like, what? I don't know, what's that mean, right? So that's like the language that we use. So there's going to be a lot of it. You're going to get used to it. You're going to get familiar with it. I'll try to make sure I'm explaining everything as it comes. If I miss it and you don't know what I'm talking about, ask me. I'll make it clear. But some of the obvious ones that maybe will come up that kind of come up around computers is hardware, software. Well, hardware is like your physical computer. Software are like the programs that are running on your computer. Input and output, I/O. Input is how you put information into a computer, and output is how information comes out of a computer. So like your monitor is output. Your keyboard is input. Processor, that's like, raise your hand if you've heard the word processor before. Raise your hand if you're like, I don't know what it means though. One honest person. The processor is basically, there's more to it, but that's like the thing, to put it simply, that's like the thing doing all of the like actual like computing and work. It's doing all the calculations and everything. There are other specialized hardware that can do that too, but in general, a processor kind of manages everything. It is like the brain, let's say, of the computer. And then you have storage. You could have long-term storage, things like a hard disk drive or solid-state drive. That's like a lot. You got a question?
This is kind of a stupid question, but is the CPU the same thing as
Yes,
the
it is. Yes. Central processing unit, processor. Yeah, it is. Good call. In fact, I should probably say CPU because that is, I think, the more formal word. Long-term storage, that's where like when you install a program on your computer, that's where it gets stored. All of like, if you've got a movie or pictures on your computer, it's stored in the long-term storage. But we also have like shorter-term storage, things like RAM. Raise your hand if you've heard RAM before. Raise your hand if you don't really know what RAM is, but you know you want more of it, right? RAM is storage, but it's the storage of information that's currently being used by the computer. So, like, you all have like Chrome installed on your computer, or Firefox or whatever, right? Some browser. You have it installed. So that is stored on your long-term storage. But when you open it up, and the computer actually needs to run that program, it loads the data from long-term storage into RAM. And the reason for that, there's some like engineering reasons for it, but RAM is quicker than long-term storage, and it's just where they store all of the information, the data and instructions of what's going on in the computer at that time. And you want more of it because you want more room. You can think of the analogy here as long-term storage is like I want to bake a cake. Long-term storage is my pantry and fridge. My countertop is RAM. and me baking the cake is the processor. I'm using the stuff I need to bake the cake, I'm going to put on the counter. So it's there. It's easy to access. I don't need to keep walking back and forth to the counter in the pantry and the fridge. If I have a bigger counter, I can put more crap on it too, right? So that's fantastic, right? So you want more RAM. You want a bigger counter. If you have a bigger pantry, you can store more stuff in it. What, binary, raise your hand if you've heard, binary before. Raise your hand if you don't know what it really means, though. So binary is simply, I could explain this a lot of different ways, but binary is simply patterns of zeros and ones. Now, it's funny, though, because, we always talk about computers. Oh, zeros, ones, zeros, ones, zeros, ones, right? But really, the computers don't care about zeros and ones. They care about low voltages and high voltages, right? The computers don't really care about zeros and ones. A zero is a low voltage, a one is a high voltage, and that's actually what's running through your computer. But binary is how we tell a computer how to actually do its thing. So if I created a program that can run on the computer in zeros and ones, I would call that machine language, because the computer knows how to run the zeros and ones. A language like Python is a much higher level language. We're not writing computer code as zeros and ones. We write print hello world and hit run, right? Now, the computer doesn't know what the hell print hello world means. There needs to be a translator that converts the Python code into the zeros and ones that can actually run on the computer. Which brings me to another point, and I brought this up in lab yesterday, and I'm going to emphasize this a lot this semester. A lot of new programmers don't know what it means to have good code. Just because it's correct, you could have absolute garbage code. It could be 100% correct, but trash. Good code, for the most part, in addition to correctness, is not, I solved it with less lines of code. I solved it, but it takes up less space. It runs fast. Good code is code that someone can understand. It's code that you write and you show me, and I know what it does. If you give me code and I go, what the fuck is this? That's bad code. Languages like a computer programming language, like Python, contrary to popular belief, is not for computers. It's for humans. It's designed to be understandable and easier to use for humans. It's designed to be self-explanatory to humans. Machine language, the zeros and ones, that's for computers. Your job is to make your code as human readable as possible, and that is a thing. Sometimes it's better to go to your way to do something the long way if it's more clear what it's doing in your code. So computer code is actually really for humans. All it takes, though, is that program that can convert the computer code into something that can actually run on the computer, the zeros and the ones, which are really just representations of low voltages and high voltages. Compiling, okay. So that's kind of like the program. There's more to it than this, but that's like the program that converts Python to the zeros and ones. Really, there is no compiler with Python. There's an interpreter, and it runs on a virtual machine, yada, yada. It doesn't matter. But traditionally, that's what would happen. And then, like IDEs, Integrated Development Environment, that is like the programming environment where we write our code in. Now, Colab, I guess, is technically an IDE. But there are other more sophisticated, heavy-duty ones that you could use, like PyCharm, for example, is a popular Python one. This is obviously not an exhaustive list of all of the fancy terminology I'll be using. And like I said, I'll try to make sure I'm explaining things as I go if I bring up new jargon, but if I forget to, raise your hand, let me know, what the hell do you mean when you say that word? Oh, yeah, I'll explain it. Any questions, thoughts, concerns? So print. So we already made use of print. Print is a function. When I say print, it means output this information. as like text. That's what print does. Now, what will it print out? Well, that is what we put in the parentheses, between the parentheses, the brackets, parentheses. The value that we put in there is what gets printed out. The thing that we give to the function, so the function is called print, the thing that we give to the function, and we're going to talk more about this later, is called an argument. All right? Sometimes people mix up the word argument and parameter. It's very common to mix those two up. People just know what they mean based on the context, but more on this in another topic. So print is a function. So for fun, if you have it available, open up Colab and just run a print again. But this time, print out whatever hell value you want. It could be another string that has like quotes where you can write something. You can just print out just any other arbitrary value. I'll give you like 2 minutes to do that. See if you can get it working. Oh no, it looks like it froze. I'm going to try to... see if I can fix it while the recording is taking place. Let's see. All right. Who knows how long it's been frozen for, but we're back. Raise your hand if you're done. Raise your hand if you'll be done in like 30 more seconds. Okay. While you finish it up, I'll just talk about mine. Here, I did it. In fact, I did it 3 times. In the first one, I'm saying print out the string, more on that in a moment, some silly message. Then on the next line, by the way, if you're trying to do this and it's not working and it's saying something about like literal 1, whatever, you might notice on the far left, and I'm bringing this up because it happens every year, on the far left of that box area, not quite as far as like the run button, but you'll see the numbers like 1, 2, 3. You don't write those. I think by default, Colab doesn't include line numbers, that you could find it in the setting, but all that is just line numbers. Which is nice when I can say something like refer to line 7, right? So you can see it. So you don't need to be typing like 1 space print. No, you don't do that. So based on this running, so I said print that, then on another line I said print 55, and then print that was a number. So each line of code is like a statement to do something. You can have lines of code that have multiple like statements kind of like in it, but it's usually better to have like 1 statement per line to keep your code as simple as possible. And judging by the print, you see, well, okay, clearly it displays stuff. And what's interesting too is notice how like it went to a new line after every print, right? They didn't like go next to each other, they stacked vertically. So whenever print's done, it prints whatever you said and adds like a new line that it can carry on. So there's an example of print. Any questions about print? Yes?
What you just said about the line Python thing, or all program languages do this?
Where it adds a new line? It depends. So print here, by default, there's actually, okay, so I'm going to answer it in detail, and then everyone in here is going to be like, what? It doesn't matter. There is a hidden default argument that is at the end of this line, add a new line. But you can change what is added to the end to be nothing or whatever you want. So by default, it adds a new line. Now, in other languages like Java, they'll actually have different functions. There's print and then println for print line. So it just depends on the language. But Python by default does that. Here's another thing too. I mean, there are multiple ways to print out multiple pieces of information. But if you want things on the same line, you can add commas to print. You can actually add an arbitrary number of things and hit run. And it'll print all those things out on the same message, but on the same line, but it'll separate them based on spaces. So we can keep going. 3, 3, 7, 7, 0, 0. 0, 0, it's going to be 0 because it's just 0. More on that in a moment. So values and types. So programs really are instructions that manipulate values, some data. And data has like values. For example, we've got what we're calling strings, A, B, C, D, E, F, G. There's another one, hello world. Those are strings. It's a string of individual characters. That's why they're called strings. Below that, I have 7, 42, 97. Those are integers. And then on the last line, we have floating point numbers. These are numbers, but they also include decimals. There are a lot more types that we will see. We can even make our own types, but that's for a later time. Here are 3 types. And it is interesting that integers and floating point numbers are like, why do they really need to be different? But there is an engineering reason why that we will cover in a little bit. One thing you'll notice about strings is they have quotes around it. And that's important for the string. Because if I didn't include quotes, it doesn't know that it's a string. It's going to say like, well, what is, like, what's that? What's going on? What is that? In order for the thing to be a string, it needs to be between quotes. Now in Python, technically you can use single quotes or double quotes. Double quotes arguably is a little bit better for a few reasons. It's also more standard along other programming languages, but if you use single quotes, it doesn't really matter. So we need the quotes for strings. Integers are just integers. And floating point numbers, well, those are just numbers, but with zeros, or with like decimals. So here's something interesting. See how like when I hit run on this one, how the last number, it was 0, 0, but it really only printed out the 0? Well, that's because the 0, 0, the thing at the far right there, it's the integer, I mean, it could be 0, 0, 0, 0, 0, but the integer value of that is still just 0. But you might say to yourself, well, no, I really want that 0, 0 to be printed out. Well, okay, you can make it a string, and then it'll print out the 0, 0. There's a lot of things we could do like this. So the values that I showed you here are technically called literals. They are literally what they are. Like when I write the number 1, it's the value 1. It is what it is. That is, and you'll also notice that when I talked about these values, I also described the type of the value. It's a string, it's an integer, it's a float. Because the difference is important. In fact, the integer 1 and the floating point number 1.0 and the string 1 are all very different as far as Python's concerned. They are different pieces of information. So the type is very important. Some errors that you will absolutely come across will be caused by mixing types. I'll give you a quick example of this right now. If I go, let's go down here real quick. If I say print 1 plus 1, and I hit run, we get 2. So this line of code here said, okay, well, 1 plus 1, well, that's the sum, that's 2. It gets calculated. And then print out the result. Well, we get 2. But if I accidentally do something like this, try to add the number 1 to the string 1, it's going to say I can't do addition on a string and an integer. That doesn't make sense. It's just a coincidence that that string was 1 and you think it should be. But like if I were to say this, 1 plus hello, Python's going to go, I can't do that. Now, one year someone asked me, like, well, why not? And it was kind of difficult to answer because to me I was like, fine, what's 1 plus hello? Tell me. Like, what should Python say? What's 1 plus hello? It's a ridiculous statement, right? It's a ridiculous question. 1 plus hello is equal to what? Nothing. That's not a thing. You can't add 1 in hello. That's not an option. So that's what Python's saying here, type error. Type errors are very common. Now, Python, a lot of reasons new programmers like Python is they get tricked a little bit. Because Python's nice, and it figures out types pretty well. You don't need to be that explicit about your types. Where in other programming languages, every time you create a value or a variable, you have to specify the type. It's very important that you do it. They're very strict. Python's a little more loosey-goosey with types. But type errors are common. And so you're way more likely to come across these types of errors, these type errors, than you are in some of these other languages where you need to be more strict. So type errors, you'll run into them. It's going to happen. If you're ever wondering, oh, OK, here's something I'm going to say. I said it in lab yesterday. I'm probably going to say it in lab today, but I'm going to say it here just so it's recorded and you can remember. Let's use the camera working. OK, good. Colab is a great programming environment, but you have to understand Colab is a tool designed for programmers. It's really not designed for learning programming. We can use it for sure, but some of the features and quirks of it make sense if you're an experienced programmer and could be at best useless and at worst insanely confusing for new programmers. And I'm going to show you an example of one. This is like one of the #1 things I hate about Colab is how confusing it can be. If you ever want to output information, like a text information, print it out. Okay? Printing is amazing. It is common to see people's codes riddled with printed out print statements or print function calls because you're concerned about what values there are. So if you ever want to print something out, use print. 1 plus 1. There, we get 2. Great. However, Colab will let you do this. 1 plus 1. Enter. And you see a 2. So you say to yourself, oh, well, it printed it out. It outputted the number 2. No, it did not. It looks like it did, but it didn't. All that's happening here, this is where Colab is being like nice. And this is a nice tool if you're an experienced programmer. But if you're not, it's confusing because it looks like it printed it out, but it didn't. If I were to run that code in another, like on my computer, not on Colab, there would be no output, even though it looks like there's the number 2. Because here's what happens. Often, a line of code produces a value. 1 plus 1 produced the value 2. But I didn't do anything with that value. So the computer has, like this program has this value 2 that's just like floating into oblivion. So it's this like dangling value. And when that happens, Colab just goes like, oh, here, look, this is that dangling value. It just shows it to you. But it never actually really printed it out. And this creates so many problems for new programmers when using Colab. And we can even make it like a little more obvious how it's different when I do strings. Print. Oh my goodness. I print out, oh my goodness. Let's try that again. Print hello, you see hello. But watch what happens when I do this. See how it has quotes this time? So it's a little bit different. The point is, hello was never printed out officially. Colab just made it seem like it was being output. So if I were to do something like this, this will make it more clear. You can see hello and hello, right? The top one was the actual correct print. And the one below was just what happens when Python goes, oh, there's a value hello that no one did anything with, so here you go. That's what it was doing. So look what happens when I run this code. Now, for those of you in lab yesterday that remember what happened, don't say anything, right? So pay attention. I hit run, okay, which makes sense. The top one, the top hello, which is the regular print, we see the string hello. And then the bottom one, oh, the fact that there's an uppercase is just me typing the wrong there. This might be better. The bottom one is it just showing it to you. Now, what will happen when I do this? I'm going to get rid of this because that's not the output. When I hit run, what would you expect to see? You don't have to answer it. Come up with an answer in your head, lock it in, and then I'm going to hit run, and you're going to tell me if you were right or wrong. Were you right? You were wrong. And here's why. Because that dangling value still exists on line 1. But dangling values are only shown in that sneaky way when it happens to be the last line of code. So if I were to do 1 plus 1, we see the 2. Whoop. And here, we only see hello. I just finished ranting about how this screws up new programmers so much. Here's how to never be screwed up by it. Whenever you want to output something, use print. That's it. Use print. All right, I'll see y'all, half of you later today and the other half on Tuesday. And it froze again. Well, whatever.